A PhD student at UC Berkeley was able to reproduce the aha moment of DeepSeek on his own model. And it turns out you can do it for just $30. So what does that actually mean? What did this person accomplish? I'll break everything down. Let's get into it. So let me talk a little bit more about the aha moment before I show you how the Berkeley student was actually able to reproduce it. So a particularly intriguing phenomenon observed during the training of DeepSeek R10, remember this is the non-instruction tuned version, is the occurrence of an aha moment. This moment, as illustrated in table 3, occurs in an intermediate version of the model. During this phase, it learns to allocate more thinking time to a problem by reevaluating its initial approach. This behavior is not only a testament to the model's growing reasoning abilities, but also a captivating example of how reinforcement learning can lead to unexpected and sophisticated outcomes. And that's the key. That is really the thing that I think we're going to see much more of in the future of these LLMs. You're going to have the base LLM trained as usual, and then the second layer, which Dario, the Anthropic CEO, just talked about, which is this reinforcement learning layer, basically giving it the right rewards for getting an answer right or wrong. Now, here's the thing. This reward can only be well-defined when we actually know the answer to something. Math, logic, reasoning, coding, right? But if you just ask it to do creative writing, there's no right answer to an open question like that. And I'll touch more on that in a bit. So this is Jai Pan, hopefully I'm pronouncing your name right, and he's a PhD student at UC Berkeley. Just a few days ago, he put out this tweet. We reproduced DeepSeek R10 in the countdown game, and it just works. Through RL, reinforcement learning, the 3 billion base language model develops self-verification and search abilities all on its own. You can experience the aha moment for yourself for less than $30. Here's the code. Here's what we learned. Okay. Let me tell you what all of this means. So one of the major breakthroughs as part of the DeepSeek paper was this thing that they called the aha moment, where this emergent capability came from the model to do this deep thinking. What they learned is that through reinforcement learning, the model started to develop this internal monologue and thinking ability all on its own. What they needed was a really good data set. And so reinforcement learning is really special. This is the same method that allowed AlphaGo out of DeepMind to beat the best Go players in the world without actually having seen any human annotated games. It basically just learned how to play Go by itself. And that is what they were able to show in the DeepSeek paper. By having a very well-defined reward function, the model was able to learn to think. What is meant by reward function is an easy way to tell the model whether it got an answer right or wrong. Now, if you have a very open-ended question, then that's really difficult to do. An example of an open-ended question would be something like, which color is best? There's no right answer. This is just completely opinion. However, for math, for logic, for reasoning, for programming, these are all areas in which there is generally a very definitive answer. And when you have a definitive answer, you could tell the model, yes, you got this right, or no, you didn't. And then the model can just try things over and over again until it gets it right more times than not. All right, so now that you understand that, imagine taking that concept and applying it in a very narrow way to achieve that aha moment. So they did that with something called the countdown game. And the countdown game is a game where players combine numbers with basic arithmetic to reach a target number. There is a definitive right answer to this. And so with that, they're able to create that very well-defined reward signal for the model. So let's look at an example of what that actually looks like in practice. So here it is. User using the numbers 19, 36, 55, and 7, create an equation that equals 65. Assistant, let me solve this step by step. So thinking, and it goes through a bunch of iterations. This is the internal monologue, and then the final answer. And that is the correct answer. And if you want to play around with DeepSeek R1 and other awesome open source models, you can do so at AWS's Amazon Bedrock. And a special thanks to AWS for sponsoring this video. And so DeepSeek R1, both the distilled versions and the full version are now available at AWS's Amazon Bedrock. Amazon was one of the first companies that had a clear vision of a multi-model future, and they are doubling down on it with adding DeepSeek. So you can now deploy DeepSeek R1 models on both Amazon Bedrock and Amazon SageMaker AI. The broad and deep range of models in Amazon Bedrock empowers you to choose the precise capabilities that best serve your unique needs. It's all about choice. And with Amazon Bedrock guardrails, you can independently evaluate your user interactions with your models. Security, safety, control, ease of deployment. Check out DeepSeek R1 on AWS right now. I'll drop links in the description below. Thanks again to AWS. So here's the recipe. We follow DeepSeek R1 algorithm. Given a base language model, prompts, and ground truth reward, we run RL. We apply it to the countdown game. The results? It just works. Essentially what they found is with a good base model and reinforcement learning with a very clear reward function, the model will start to think for itself. And that is so crazy to think about, especially because they were able to achieve it on such a narrow domain. And so maybe that's the future. We've talked about test time training in the past, and more people are starting to talk about that right now. That is essentially the ability for the model during inference time to adjust its own model weights based on the prompt. So imagine that combined with test time reinforcement learning. I don't even know if this is possible. I'm just speculating here. But imagine a combination of these things in which you can have insanely small models solving really hard tasks because they are so specifically tailored to whatever that task is. So let's walk through the process. The model started with dummy outputs, meaning it was just completely wrong or nonsensical, but gradually developed tactics such as revision and search. And this happened naturally. No nudging, no need to say, here's how to think through it. It just arrived at this thinking. In the following sample, the model proposed a solution, self-verify, and iteratively revise until it works. He also provides a weights and biases link in which he gives you the full experimentation. If you want to dig into that, you can see it yourself. And so that's what this looks like. You can actually see the performance over time, each of the steps of the reinforcement learning, everything. Now, one of the findings is that the base model quality is key, and he tried it on Qwen 2.5 base with 0.5B, 1.5B, 3B, and 7B. 0.5B guess a solution and stop. But once they reached 1.5B and up, the model started to learn to search, to self-verify, and revise its solutions. So that's what we're seeing right here. This maroon color line is the 0.5B, the model that wasn't good enough to quite reach that thinking capability. So what we see is a little bit of an uptick in performance, and then it flatlines. However, the other ones really jumped up high, and as we see, the bigger the model, the better their performance overall. So the starting quality of the model is really important. And either the base model or instruct model works. Instruct model learns faster, but converges to about the same performance as the base. The instruct model's output are more structured and readable. So extra instruction tuning isn't necessary, which supports R10's design decision. Now remember, the R10 is not the instruction tuned model. So with DeepSeek, you got two. You got the base unwieldy R10, and then you also got the just R1 after they kind of put the final touches on it. And so that's what we see here. In yellow, this is the base model, starts a little worse, but pretty much ends up at the same place. And then the gray starts a little better and again ends up at the same place. And he also found that the actual reinforcement learning algorithm that you use doesn't actually matter all that much, which is really interesting. These are such cool findings, and DeepSeek kicked it all off. And that is the power of open source. Now, obviously, there have been people who already knew about this stuff, but once the DeepSeek paper was published, once people saw how good that model is and could actually read how to reproduce it, everybody started tinkering. The power of open source. So here we go. He continues with the specific reinforcement learning algorithm doesn't matter much. We tried PPO, GRPO, and Prime. Long chain of thought all emerge and they seem to all work well. We haven't got the time to tune the hyperparameters, so don't want to make quantitative conclusions about which algorithm works better. And the model's reasoning behavior is very task dependent. So for countdown, the model learns to do search and self-verification. However, for number multiplication, the model instead learns to break down the problem using distribution rule and solve it step by step. So interesting. So it really changes its behavior based on the task at hand. That's why I go back to, what if the future is really, really small models doing all of this reinforcement learning, test time compute, test time training at inference time. It's so cool to think about. We're going to have hundreds, thousands, millions of these tiny models that can just be hyper-tuned to very specific scenarios. Now, a caveat he leaves at the end. This is only validated on the countdown task and not general reasoning. We are bounded by compute. Now, in this thread, the author answered a bunch of questions, and I want to go over some of those to give you even more detail into how cool this really is. So here, any insights on why OpenLlama achieves high response length, but low scores. OpenLlama doesn't like to generate EOS tokens, and since we haven't implemented stop after the /answer, the model often fails to terminate. We didn't report OpenLlama's results in the Twitter thread as we believe the results will improve significantly once we fix this problem. So again, it doesn't really matter what model you're applying this technique to. It doesn't really matter which reinforcement learning technique you're using. Of course, there's going to be little optimizations here and there, but this is so exciting because it's such a generalized emergent capability from reinforcement learning. All right, one question, what model size and algorithm do the $30 refers to? 3B model, 3 billion parameter model, PPO reinforcement learning, and it takes 10 H100 hours, which is the $30. So another question, do you have any observations regarding the chain of thought length changes during training? Is there a plot showcasing chain of thought length increase during training? Great question. Early results show the 3B model initially reduces output length for correct formatting, then increases chain of thought length for better performance. Here is what that looks like. So initially drops the output length down, then learns long chain of thought, and it kind of stays equal, maybe drops a little bit over time. Now, here's an interesting question. Do you find the original paper's numbers about the training cost to be plausible? Yes, with mixture of experts and FP8, floating point 8, that's expected. And that's exactly what Dario, CEO of Anthropic, just said in his paper. So if you want to play around with this, he open sourced everything. It's called TinyZero. I'll drop a link to the GitHub down below. The data set, the weights and biases run, everything is available. Open source wins. If you enjoyed this video, please consider giving a like and subscribe, and I'll see you in the next one.